Welcome to this video on advances in mechanochemistry, focusing on two paradigms of mechanochromism, from covalent bond homolysis to innocent piezochromism via single electron transfer. Mechanical force has evolved from a source of unselective degradation to a precise chemical trigger. Mechanophores now transduce macroscopic force into programmed optical or chemical signals, eliminating the need for complex electronic sensors. Generating stabilized free radicals relies on two distinct mechanochemical pathways. Paradigm 1 is covalent bond homolysis, which is destructive and tension-driven. Paradigm 2 is innocent piezochromism, which is non-destructive, compression-driven, and relies on single electron transfer. Covalent homolysis relies on thermodynamic stabilization to lower the activation-free energy of targeted bonds. The COGEF model suggests that activation-free energies decrease linearly with applied force, with a threshold of approximately 5 kilocalories per mole. Dynamic covalent motifs like DABBF and DABBT offer exceptional autonomous reversibility for continuous stress reporting. They feature CC-cis bonds and allow sterically unhindered radicals to autonomously recombine at room temperature. Here we see the chemical structure of DABBF and its transformation upon mechanical stress. Rigid homodimers like DFSN and TAZN overcome the thermal instability of early mechanophores. They act as sacrificial toughening agents, dissipating massive strain energy to increase tearing resistance. These diagrams illustrate the radical formation of DFSN and TASN, as well as the concept of forming double and triple networks to enhance mechanoreactivity. Moving beyond carbon-carbon cleavage, force-induced heteroatom scission initiates active secondary polymer cross-linking. HABL involves a CN-cis bond, and a 2024 breakthrough demonstrated productive, force-activated solid-state organic synthesis. The HABI system shows the transition between the associated, colorless, fluorescent form and the dissociated, colored, non-fluorescent radical pairs, with the off state having an absorption maximum at 604 nanometers. Innocent piezochromism introduces pressure-induced color transitions without breaking any chemical linkages. Extreme hydrostatic compression causes a transition from a pale yellow powder to a deep green state. These are the structural representations of the components involved in the innocent piezochromism mechanism, including the 4,4-bipyridinium and carboxylic acid units. Extreme hydrostatic pressure, up to 3.62 gigapascals, forces geometric contraction, driving spontaneous forward electron transfer. This forced proximity elevates quantum orbital overlap, eliminating the activation barrier and instantly generating the stable viologen radical cation. The chromic sponge phenomenon links solid-state mechanochromism with hydrochromism. Dehydration mimics compression, triggering spontaneous single electron transfer, and a color change to deep green, which reverses upon hydration. Kinetic mismatches and dispersion forces stabilize the metastable radical state at ambient pressure. This includes ultrafast electron transfer timescales and Pymer bonding, where immense London dispersion forces overcome expected Coulombic repulsion. Acoustic and fluidic innovations translate viologen redox chemistry into dynamic supramolecular patterning. Innovation 1, mechanical shaking, introduces directional oxygen diffusion for cyclic disassembly and reassembly of chiral nanotubes. Innovation 2 uses low-frequency acoustic manipulation, or 40 Hz sound waves, to create localized liquid vibrations. This dictates the selective dissolution of gases and results in sustained spatiotemporal patterning of host-guest complexes. The physical chemistry dictates strict structural matrix constraints. Covalent homolysis requires flexible elastomers, where polymer chains act as levers to funnel tensile strain. Viologen set requires highly ordered molecular single crystals, as random dispersal destroys the precise geometric proximity needed for quantum orbital overlap.